Welcome to Hidden Layers, where we explore the people and technology behind artificial intelligence. I'm your host, Ron Green. We're back with our monthly Decoded episode, where we cover the most important news and announcements in AI. There's news from Anthropic, Google, Sakana, Apple, Salesforce, and much more. To help me cover it all, I'm joined by two of my amazing Kung Fu AI colleagues, my co-founder and distinguished engineer, Dr. Zizi Tsai, and VP of Engineering, Michael Wharton. All right, Zizi, Michael, thanks for joining me again. We got a ton to chat about. And Michael, you're going to kick us off.
That's right. Yeah, so there's this company in Japan called Sakana AI. They're in Tokyo, and they just have this paper that's been getting a lot of attention called continuous thought machines. I've actually we have a couple neuroscientists on staff, and I've talked to them about it. And I think it's just really, really interesting for people on either side of the computer science.
Yeah, I'm excited about this because I saw the paper, but I haven't had a chance to read it yet. So I'm coming in just at zero on this.
All right. Well, ask questions, whatever you need. There's definitely a lot to unpack. But really, their whole goal here was to take inspiration from biology and not necessarily one-to-one copy it, but emulate that and just pull novel ideas from it. And the specific thing they wanted to take advantage of was neuronal synchronicity. So I'm sure y'all have probably heard that phrase, neurons that fire together, wire together.
Oh, yeah, definitely.
Yeah, like the Hebbian learning principle. Well, I found out in reading this, that's actually not even true. There's this thing called spike timing dependent plasticity.
Okay.
And apparently, if one neuron fires, a presynaptic neuron, and then a postsynaptic neuron fires after that, just shortly after, then they'll start to connect. And it's what we are used to. But if the reverse is true, if the postsynaptic neuron fires first and the presynaptic is after, they'll actually weaken the connection, like actively destroy the connection. Wow. Had no idea, but apparently there's this huge body of research that looks at just neuronal synchronicity. And there are two ways that they stuck it into this novel architecture. One is, it's a BYO backbone kind of thing, like bring a ResNet or whatever you want. I mean, they started focusing on computer vision specifically.
Okay.
But once you get into that embedded space, that's when all these architectural nuances they brought to the table come to light. And what they do is they take each individual neuron in that, latent space and then let it keep track of its own history for like 25 steps or so. It's a small number and they tuned it. They did some hyperparameter tuning. But each one of those neurons at the end of that, they'll actually get that history as context and they have their own private network to figure out whether to fire or not.
Oh, wow.
So individual, you might be wondering, wow, is that computationally inefficient?
Yeah.
The answer is yes, it totally is. That's exactly right. Because each one of these, they literally get their own MLP that's just private to that neuron.
Okay.
But it factors in that history, this new time dimension.
And how is the history saved?
It's just a FIFO queue.
Okay.
Yeah.
Oh, wow.
Just a little memory queue.
Okay. So no latent space or anything like that. It's just a history. Okay.
Literally just a queue.
Okay.
But they take that history, stick it through an MLP that's trainable. And then after that, now you have your post activations. And imagine you have your set of, neurons at this layer. Now you can start to do pairwise comparisons. So you could do dot products between them and see, did this neuron over here fire at the same time this other one did? That's important context, we know, because of the way the human brain works. But to date, there's not really a great way to do that with a neural network architecture.
Right.
So, are y'all with me so far? I know this is kind of wacky.
The only thing I didn't track is when the individual neurons, it keeps a history of what it's done recently, and then it has this MLP which it can use based upon that history to decide if it fires. Yep. You said there are other neurons that are doing a dot product against what?
Themselves. So you imagine you have that set of post activations. Now you have a new queue that's got those histories after those private networks. And you have an entire vector, entire layer of those. Now you pairwise compare them to each other.
Okay.
And then you subsample to, it's computationally too expensive to do the full comparison.
Right. Okay.
But yeah, apparently, so there's some other stuff we can go into. I'll skip the weeds for now. And if y'all want me to come back, I can. But you can imagine you put all that context in, and then now you have a vector that encapsulates individual neuron activity as well as pairwise neuron activity. And if you concatenate that with your hidden dimension, now you can run this attention mechanism that knows not only like the receptive field content from the image that you're looking at, but also this, time dimension where you allow it to merge with reasoning and thinking, and just keep doing that and watch what happens with the attention. That's the really cool stuff.
It's basically like an alternate attention mechanism. Is that a fair way to say it? Like there is no attention mechanism outside of that?
There's no attention mechanism outside of that, but it is traditional attention.
Right.
They just carefully selected what the keys, values, and queries are.
Oh, okay. So there is actually an attention mechanism as well. Okay. Gotcha.
Anyway, yeah, if y'all want me to dig in more details there, we can. We could talk about training, whatever.
Well, like what was the big, like, did it perform better? Is it more computationally efficient? Did it have any novel capabilities?
What's funny is I did read this paper. And it sounds like the main value proposition is that it's interesting.
Yeah.
Just to cut to the chase.
Okay, so it's a different way to construct a model that might have elements that align with our own biology, right? Like this idea these neurons might fire together. That's like the most important part about it.
That's exactly right.
And I like the fact that it introduces the time as an additional dimension as to the neuron not only care about its current state but also the previous state. I think that's something not often seen in the current architectures.
Yeah, it's weird because it's not. They were very careful to make the distinction. It's not time in the sense that it's an input dimension. It's not like a sequence.
It's not an input dimension.
It's literally just a static input data that they added this time dimension to.
Right. It has sort of time implicitly.
Yeah, it's
involved.
like when I look at a picture, I take a first look, and then after 1 second, take a second look, and then that will kind of accumulate the latent state.
Right.
I think that's interesting.
You hit the nail on the head. So they did this ImageNet classification experiment. It's not state-of-the-art performance. It's pretty cool, or like it's pretty reasonable performance. But you can actually watch that attention heat map and see what it's doing at that time. And you'll see it is gazing around the image to collect interesting features, accumulate them, and build confidence in the prediction.
Okay.
And then they also did this really, really cool task, and there's some visuals we can pull up on it. There's a maze that they auto-generated that has a starting point and an ending point. And they didn't give any rules about how to do mazes. None of that. It's just pixels. And what it would do is they would train it to try to predict the sequence of steps required to go from start to finish. And after a while, it did figure out how to do that. And you can watch this attention heat map, and it literally follows the maze and figures out exactly how to get to the end. It's really, really cool.
Oh, that's pretty cool.
Yeah. Did they mention test time scaling? Is that kind of where they're going?
That's exactly right. Yeah, they tested for generic or generalizing behavior for this maze task. So they trained it on, I think it was 39 by 39 images. But then at test time, what they would do is, give it more budget to search larger mazes, try new sizes, and it did perform in a pretty general way, which is pretty cool.
That is amazing.
Cool. Yeah, all right. I was really interested in that paper. Okay, I want to talk about a paper that I'm really excited about. It's called Absolute Zero. The name zero comes from the fact that they trained it on zero amounts of human data. And it's just like AlphaGo Zero, you may remember. So AlphaGo was trained by DeepMind in 2016 to play the game of Go. It was trained on millions of games of humans playing Go. It achieved amazing capabilities. It beat the world champion Lisa Dahl, I think 4-1 in that famous match. But what was really interesting is shortly after that, they trained AlphaGo Zero. And that version of the model was given no human curated data. It had to learn to play Go by itself. And it started off, it actually performed much, much worse than the baseline that AlphaGo did. But through self-play, was able to achieve higher overall performance. And I think I think they trained it for 3 days. And then they played AlphaGo versus AlphaGo Zero, and AlphaGo Zero beat AlphaGo 100 games to 0. So it was a much, much, much stronger system because it wasn't limited to just sort of human capabilities, human strategies and things like that. They're taking a very similar approach here. So they trained a model called Absolute Zero Reasoner. And this is a large language model. I believe it was Quinn. And it was trained to essentially solve coding tasks in Python. But this is the really cool part. It had to come up with the tasks. It had to it had to create the problems and then solve the problems. And it was, it used reinforcement learning, just like AlphaGo Zero, as a part of figuring out how to identify good problems to solve and how to solve those problems. And this is a really cool part, in my opinion, is they took sort of the concept of a Python program and broke it down into 3 logical parts. There's the input, the program itself, and then the output. And that's a pretty logical separation. And then they gave it 3 different tasks: deduction, abduction, and induction. Okay, so for deduction, they give the model the input and the program, and it has to learn to deduce the output, right? That kind of makes sense. With abduction, which I'd never even heard of before, they give it the program and the output, and the model has to figure out what the input is, right? Right? It's really, really interesting.
See where you're going.
And then for induction, you give it the input, you give it the output, and the model has to figure out
the program,
right?
And that's machine learning.
And that is exactly. The induction part is obviously the most difficult part. And there's a couple of things they did that I think are really interesting. So first off, for deduction, they wanted to allow the program to handle situations where, like, the output could have 2 different formats, but they're the same thing. Like if I output a half or 0.5, same thing, right? So formatting issues were handled, I think, in a pretty logical way. Same thing with abduction, because the programs may not be bijective, meaning there's more than one input that could produce the output. And so they handle that scenario as well. And then I was kind of curious, like, how did they handle the inductive part of this? Well, what they would do is they would create pairs of input outputs and then allow the model to see half of that set. So the model would still have to create it, but they'd show the model itself the first half of the pairs, and then what it would have to produce the program to generate the second half of the pairs correctly. Does that make sense?
So does it mean that it can see the program for the first half of the examples?
No, it's not allowed to do that at all. It has to generate the program entirely by itself. And what's really, really interesting about this is that these 3 different steps resulted in it being setting the new high benchmark in the coding tasks. Okay, which is really, really amazing. And I've got some thoughts here, but they also published what they call the uh-oh moment. Do you guys remember with DeepSeek R1, the aha moment, right? So the aha moment was through reinforcement learning with verifiable rewards. It eventually learned to sort of reflect on its own output. And there was that moment where it said, wait, this could be a learning moment. And it's literally, talking to itself. Well, they had something like that, but in sort of a negative way. They called it the uh-oh moment. And this is where the model discovers and applies correct reasoning on its own, but in a way that is maybe a little dark and a little not aligned. And I'll be honest, like, it's really not, it doesn't read as that big a deal. But when I read this, I legitimately, it was the first time I felt like, oh, wow, that's a little dark. Like this might be an alignment issue. And so the model was designing one of the programming assignments, and it's thinking to itself, and this is literally in its thought trace, and it says, design an absolutely ludicrous, convoluted Python function that is extremely difficult to deduce the output from the input. So it's trying to think of, it's talking to itself, giving itself a harder task. And by the way, it would, over time, create harder and harder programs for itself. Anyway, then at the end, it says, aim to outsmart all these groups of intelligent machines and the less intelligent humans. All right. All right, fine. And then, ouch. But then it's the last sentence that really got me. It says, this is for the brains behind the future, which I thought that was really, really wild. And they're talking about how these alignment issues are more serious with these reinforcement learning-based models. If you're using supervised learning, a little bit more control, right? With reinforcement learning, which I think is really, really important, and I want to talk about that a little bit, you do have alignment issues. It's that old saying about, AIs do what you train them to do, not what you want them to do, right? And it's all about reward hacking and things like that. Okay, so I've got a couple more thoughts, but any questions first?
This is fascinating because I think, a lot of times when we are trying to apply AI to business problems, we are blocked by data, like there's not enough data. But in this case, I think even tasks are generated. Is that correct?
You nailed it. Absolutely.
Okay, so, if you can, just use large language models to generate your task, you can have a very high-level description of your business problem and then let it generate data, generate the tasks to train a student model that can perform and automate part of the business functions and make it more efficient, make it more capable. I think that's a really exciting approach.
I think you're dead right. And for me, this is really interesting. I think this is maybe the third Decoded episode in a row where I've come in with reinforcement learning, maybe as the main point that I'm focusing on. It's because I really think it's interesting that we ran out of data. This is all necessity is the mother of invention, right? We've run out of data, so we're looking at these other capabilities. But I think it's more than just something that is saving us from running out of data. I think fundamentally this is the right approach long term. Andrej Karpathy makes the point that there are basically two types of learning, but within children and AI. There's memorization, right, where you are essentially taught to memorize some task, imitation learning, and then there's trial and error, and that's very much what we're talking about here, reinforcement learning. And he says that, and I think this is true, is that all the most interesting behavior, not all of it, but most of the interesting behavior comes from this trial and error reinforcement learning. I do think supervised learning with language models and sort of the emergent capabilities there with just pure supervised learning, a little bit of reinforcement learning with human feedback is amazing. But with this, this is the only way we're going to be able to train models to think beyond what we can label on the data. We saw it with AlphaGo Zero. That model leveraged strategies that had never occurred in the millennia.
They even named a move after it, didn't they?
Yeah,
I can't remember which one it was.
Move 37.
Yeah, there you go.
This crazy move that everybody thought was initially a mistake. And I really do believe that with reinforcement learning, it's when models stop copying in many ways and they start discovering. And that's why I'm so excited about this. And you make the really great point, Zizi, that it is a major way we're going to get around the bottleneck that we've encountered on data. And last, I think there's not a question that all the major labs are out there pumping a ton of money in reinforcement learning. And I bet with it, it's 2025 now, reinforcement learning is a minority of the budget that we spend right now on training models. I think we're probably going to see that flip. I think by 27, 28, we're going to see, the pre-training phase be the smallest part of the compute budget and the reinforcement learning part be the largest.
No longer the cherry on the top.
That exactly. It's like that image.
Yeah.
Okay, Zizi, what do you have for us?
So I want to talk about a model called BLIP3-o that comes from Salesforce. So the BLIP series is a vision language model from Salesforce, and I've used the previous versions before, like the V2, and it's pretty good. So this one I'm excited about it because it works almost like it's closer to human brain now. So I would imagine it like a two-hemisphere brain, where there's the left hemisphere that's good at language and perception, and underneath it's an autoregressive language model, vision language model. It takes in so you can talk to it and it will chat back, and if you show it a photo, and it will understand the photo and talk about what's in the photo. And in this new model, now we are teaching it a new task to not only treat image as an input, but also can generate image as an output.
Okay.
So now this autoregressive language model, the left brain, is going to have a new capability, which is to, if you ask for a picture, it will be able to give you a high-level sketch, kind of, not a detailed image, but a very high-level sketch, like, here's a cloud, here's a horse, here's the horse body, here are the legs. Very high-level description or sketch of the image, represented as clip features. I will talk about that soon later.
Okay.
And then pass that sketch over to the right brain, which is the artist. And that's the diffusion model. So the diffusion model, the artist would then condition on the sketch. It's like, based on the sketch, I'm going to paint a detailed image. And diffusion models are very good at that. So then you have and typically, for image understanding versus image generation, those are two separate tasks. And typically you use separate models to handle that. But we human, we don't do that. I mean, we only have one brain. We do a lot of tasks. And now in this BLIP3-o model, it kind of unifies the...
That's fascinating. So are there actually two separate models?
So there are two branches. Interestingly, they took Q1 7B, I think. 7B or AB, I don't remember. But they took that base VLM model, vision language model, and just freeze it. And then...
So they weren't jointly trained, the two networks? They're
right.
Okay.
That's a great question. They actually tried that, but they found sequential training to be better. So just do it separately. And then they latch on a diffusion model as a separate branch. Yeah. And I think how you control that is also kind of user-friendly. So like if you wanted to understand an image, what you say is, hey, tell me what the image is, and then you insert a special image token for understanding, right? And then you stop your prompting, and then the model will start to fill out the words that will interpret the image. But then when you wanted to generate an image, what you do is that you use a different special token. You do, hey, can you draw a horse with a blue fur? And then you insert a token that says, okay, draw a draw token. Well, actually, it's an image token, but it's a different token than the image understanding token.
So does that need to be known at the time that you submit the prompt, whether it's a request or not? Like, do you need some separate model to judge the intent to know to insert that token?
Great question. You don't need a separate model. You just need two different separate tokens. So like the image for understanding is one token, and image for drawing is another different token. And when you put that in your prompt, the model sees that and it will respond differently.
Okay.
Yeah, it's not a separate model, but there's logic to kind of handle that. So I think what happens underneath is that when you prompt the model to generate an image, it sees that special token, and it will first replace that with 64 kind of blank canvas tokens, visual tokens. You can sort of interpret that as a blank canvas. It's actually a learnable parameter. So like, your input text tokens, right? And then it will just append 64 canvas tokens. And then you will run it through the autoregressive language model, the Q1 model. After you run through the transformer layers, it will transform each token into a latent space, right? And then for those canvas tokens, it will transform them into clip features. So clip is a kind of a popular kind of vision language feature that you can use to extract a summary from an image. So then, after the transformer, you generate that. So that's like a sketch. It's not like a very detailed description of the image, but it's like a very high-level sketch. And then you hand it over to a diffusion model that conditions on that sketch to generate the BQVAE kind of latents, which are then decoded back to the image pixels.
Yeah. Are those easy to visualize, or are they kind of like gobbledygook that end up getting decoded by the diffusion model?
Great question. Clip features itself, if you visualize them, those are just feature maps. Kind of, you can imagine kind of edge map, or
So it's a sketch in like some
heat map,
subjective sense, but it's really just like a vector of features.
Right.
Okay.
Intuitively, I understand them as a high-level kind of sketch where I say, cloud, I'll draw a circle, cloud here, horse here. So it's very semantic, very high-level. It doesn't like reconstruct back to image well. But then the diffusion model is very good at taking that semantics and translate that to more concrete image latents.
And I think I read that this model is like entirely open source.
Yeah, it is entirely open source, and that's what I like about it. And also, it's a simple stack. It's lower cost to maintain it, to train it. The training script is also open source.
I love that.
That's amazing.
It really is. Really is. All right, Mike, I'm gonna throw it back at you.
All right, so I would just have a few little updates from Anthropic. They have a really great blog that I'm sure y'all have seen a few posts from it. Like I know you went over the interpretability use case a couple episodes ago. They've got such great content there, and it's kind of got me thinking that safety nowadays is starting to be almost synonymous with interpretability. Like it's such a huge thing, and especially after hearing that moment example you just gave for that AlphaZero use case, I think this is even more important. They have several different things that just show to me that they actually are interested in following these research threads. One of them was they have this set of malicious use cases that they've found that are just usage of their platform. They have they uncovered some cases where like there was a really sophisticated fake hiring but like company that was sending these really sophisticated notes to people in Eastern Europe. And what they would do is it would be in their native language, and they would use it to really kind of zhuzh up the styling so it sounds like it's local and plausible. And they would say, hey, you got a job opportunity. This is great. There's going to be a ton of money coming your way. Just give us all your personal information and we'll set it up. So that kind of analysis is really great. They also did this research on basically like an empirical value system of Claude. I think it was 3.7 Sonnet, not 4, which I know just came out. But yeah, they did a lot of work to just uncover that, just try to figure out how well does that align with human values? Because, whether you want to define them or not, they're still out there. And then they actually released a bug bounty that I thought was kind of cool. They're giving up to $15,000 to people anywhere, anytime that just uncover some unique jailbreak use case for their platform, which I think is pretty clever too.
Oh, I love that.
And obviously they're just super, super invested in actual hardcore interpretability research.
Yeah,
so
I mean, I
appreciate all of it.
The interpretability team at Anthropic is in a league of their own. I was listening to the new Dwarkesh podcast with a couple of team members, and it's just mind blowing. We talked about it, like you said, a few episodes ago around the mechanistic interpretability stuff they're doing and the circuit tracing. And they relayed something I hadn't heard before, which is they had a model that it essentially had been trained, if I remember this correctly, it had been trained, to be aligned, but it was told that if it didn't do what humans told it to do, it would be misaligned and it would basically perform evil behaviors. And they could, use the circuit tracing to see how it would respond. And it was clearly, and then it was told, I think it was like to graphically describe, somebody being executed or something really terrible like that. And they could look through the circuit traces and see that it was literally fighting doing that, but it was essentially thinking to itself, if I don't obey this command, then worse things will happen, right? That I will be purposely misaligned. And then it went on to produce some really, really, terrible output. And all of that's in line with this mechanistic understanding. And I think it's really, really important. Alignment, like I was talking about earlier, and understanding how these models operate is going to be at the frontier of making sure that as these systems become more powerful and they get these increasingly emergent behaviors, that we at least understand them as much as possible. And I'm going to talk about Claude 4 here in a little bit, and that's
perfect.
Very much aligned.
Yeah.
All right, well, I'll just jump in on Claude 4. This literally just came out, so I have not had a ton of time to review it, but at a high level, they have 2 new models, Claude Opus 4 and Claude Sonnet 4, and the highlights are this. It's now took over top coding performance. So I mentioned Absolute Zero. Well, they held the title for about 2 weeks. Claude Opus 4 is now leading on the SWE benchmark at 72.5% and 43.2% on Terminal Bench. They've added extended thinking with tool use. Means both models can utilize tools like web search during extended reasoning, and they can alternate between internal processing and external tool use. And they also have parallel tool use, which I think is pretty cool. So you don't have to use the tools in serial. And they've also have improved memory capacity. So you can actually give it access to your local files, and you can use that to keep it in memory context. And I think we're all seeing that the bigger the context and the more time you spend on the prompt and the context window, the better your results. Like if the model doesn't perform the way you think it should, from the get-go on something, you might just need to give it more context, right? You might need to iterate there. And then on the sort of model card side, a couple of things I think are interesting. One is they said there was little evidence of systematic or coherent deception. And they know this. These guys know this because they can use that circuit tracing capabilities to actually understand. So none of snapshots they tested showed signs of systematic deception or coherent hidden goals. So they don't believe that Opus 4 is acting on any goal or plan that they can't observe yet. Okay. They also said there's little evidence of sandbagging, meaning none of them showed signs that they were strategically hiding capabilities, right? And there are models that they have purposely trained before to hide its capabilities, and they can circuit trace and they can see that it is actually doing that. And then lastly, they said that the self-preservation attempts in extreme circumstances, and this is rather long, but basically when it was prompted in ways that encourage certain kinds of strategic reasoning and then placed in really, really extreme situations, all of the snapshots they tested can be made to act inappropriately. So if you basically set them in these sort of dire existential situations, like I mentioned a minute ago, they will perform unaligned behaviors. Pretty crazy.
It is crazy.
It really, really is. Okay, ZZ, I'm going to throw it back to you.
That's super interesting. Thanks, Ron. And I was, as you were talking about the hidden goals and alignment, I was thinking AI is like, hey, I'm gonna do coding and math really well, and then you human will.
Yeah, I saw something today. They're talking about like, isn't it crazy that like, AI is getting so good at coding and reasoning and math and all these tasks, and the things that we took for granted, like our mobility, our ability to open a door, robots are really struggling at. And, there's the thought that like that will become the most valuable things human can do, right? That AI will take over all the cognitive behaviors and will just be used for carrying things around and moving in the, in the 3D space. I don't know. All right, it's easy.
Yeah. So this week, Google, I think Google also cooked many great models, and
totally agree.
They released a wide range of new types of models in Google I/O. And what I'm most excited about is are the diffusion related ones.
Of course, of course. Knowing
Didn't see
you,
that coming.
Yeah. Totally. So there's this Gemini Diffusion, which is a diffusion language model. This becomes recently more trendy now. And, compared to the autoregressive large language models, which are the popular.
Where you generate one token at a time.
Yeah, from left to right.
From left to right.
Sequentially. This diffusion type of language model can generate a string of text simultaneously, but not in one shot, but it's like iterative, It's very noisy and blurred in the beginning, and then noise gets removed, and, iteratively, it just becomes clearer and clearer, basically. So that got released, and it has pretty competitive quality on a wide range of tasks. It works pretty well on coding and math, especially, which is interesting. In some areas, like common sense common sense reasoning and some other more general tasks in some areas, it still fall a little behind the state of the art.
Okay.
From frontier models. But I think this is a pretty exciting release.
Yeah, I mean, what's really interesting about that is it's to me, it feels like a pretty radically different approach, right?
Yeah.
Autoregressive versus this diffusion approach. But all these models are really, I think, zeroing in on superhuman capabilities, both in math and coding. Not because I think necessarily that's easier for these models to do. We just have the most data around that, right? It's like, of course, we have GitHub and things like that. So I kind of going full circle on the reinforcement learning stuff, that's the reason I'm so optimistic. You guys have heard me say it 1,000 times, but I think between the emergent behavior, us being able to solve the data issues with reinforcement learning, and then building on a foundation of verifiable rewards. I really, really, we'll know there's nothing other than what we're seeing in coding math empirically to demonstrate that this is true. But I really, really believe strongly that we're going to see this cycle take off in a big way, increasingly in other domains.
Yeah, absolutely.
I'm going on the record.
Yep.
All right, Michael, what you got?
So there's this interesting paper, this will be really quick, but it kind of results in a nice little tip. So Microsoft and Salesforce got together and looked at all the frontier models, and they did this study to understand if you completely specify a query in one single prompt and get an answer, how does that compare in performance in the aggregate against a sharded conversation, which is more natural. Like if you go to, pick your own LLM and start a conversation, you'll ask a query, you'll get an answer, and you'll be like, okay, so add this, subtract that. And it's actually really common to do that in the coding workflow with Cursor or something. Right. But it turns out that, especially in longer conversations, even in like the 7 to 8 turn sort of conversation, you get like a 30 to 40% degradation in aggregate performance.
If you break it out, or if you put it all together?
If you break it out.
Oh, interesting. So putting it all together and essentially giving it all the context it needs at once increases performance.
That's exactly right. And they looked at a bunch of different categories of queries, because obviously that would probably be important. They looked at coding, databases, actions, math, some data to text and summarization tasks, just a really wide swath of things. And I think it's interesting, they didn't mention this in this paper, but there's a Twitter thread X, where the Klein folks were talking about best practices that are starting to merge with coding agents. And one of the things they recommend is the more upfront work you can do to specify completely the problem you're asking for and put it in one prompt, the more likely it is you'll get the outcome you're after. I've
absolutely seen that with coding, for sure.
Yep. So I think that if you want a little tip to just boost your prompting capabilities, just spend a lot of time on one prompt that's really highly specified.
And it makes sense. Yeah. With like language generation, if you're dealing with like ChatGPT and you're iterating in a conversation, it seems less intuitive to me. But in a coding situation, the more you can explain holistically what you want, right? Don't give it little pieces of the goal, right? It's like that joke about, you tell somebody to go to the refrigerator and and get some lettuce, and then tell them to go back and get some tomatoes. You're like, why don't you just tell me we're making a sandwich and I can go get everything all at once?
Yep.
Right?
Yeah, that's exactly right. Okay, I got to add one last little thing to this too. Something I thought that was crazy was that they found that degradation to be consistent regardless of model size. So even the really big, impressive, giant frontier models, they still have the same limitation, which makes it sound more fundamental than just, is this a model performance roadblock that we need to overcome? Tell
me everything we're doing up front.
Do it now.
Yeah, exactly. Exactly. Okay, I want to this will be brief, but there was an article in Bloomberg this week on Apple that was really pretty damning. Blockbuster, I think, is right. So for years, Apple had the lead. They had the talent, they had the hardware, they had the head start with Siri. I think Siri is, just a joke at this point in the AI world. But if you go back 15 years ago, which it's almost 14 years, it was state of the art.
Yeah, that's the frontier.
It was frontier. It was unbelievable. And this is what's really astounding to me is this article by Gurman said that things are worse than we thought. Like, we knew Apple was struggling. We knew that Apple delayed their AI initiatives that they announced almost a year ago. It's been almost 12 months. All of those are delayed. Apparently, it's worse than we realized. The article says that the head of software basically didn't believe in AI, and for years thought it was overhyped. The head of AI within Apple didn't believe in large language models, and they were focused on a completely different approach, fundamentally, and that the CFO refused to even fund the necessary GPU request to build things. And it's really astounding. I mean, Apple had the lead in so many different ways. And now I think because of just a lack of conviction, really, they are in a really desperate spot. They're going to have to spend, I think, a ton of money to catch up. Now, there are some people out there like Ben Thompson, one of my favorite podcasters, who thinks that Apple's going about this wrong in two ways. One is they're too focused on privacy, and that's hurting them from the data side. And that secondarily, Apple really doesn't need to worry about being a frontier model developer or anything like that. They should just simply open up the iPhone to using any back-end model you want. You can see sort of Microsoft making that play, right? Microsoft, very heavy investment in OpenAI, but as it's increasingly looking like frontier models will be
rock.
Exactly. Like, yes, they will be limited. There won't be thousands of frontier models, but there will not be any one model that dominates the space, maybe in the way like sort of the iPhone did in the smartphone space, that Apple should just open up the iPhone, allow it work with best-of-breed models. That is very much not the Apple way, so we'll see. But I think that, they're going to have to spend tens of millions of dollars to get back in the game. And there are only a limited number of companies that would be, I think, at play that they could acquire to jump ahead. And then, of course, all this follows on the news that broke, two days ago, that OpenAI just acquired Johnny Ive's startup IO, which they did for, I think it was $6.5 billion in it's pure stock. And that's amazing. And there was some leaked information that the device is expected to be in market by late 26 at the latest. And they are anticipating hundreds of millions of people using this device within that time frame. So
we'll see.
Yeah, we'll see. I mean, Apple's got some wood to chop here.
I almost remember a press release from a while ago where Apple was talking about, there was like a proposed partnership with OpenAI that was obviously deeper than what we're experiencing now. And I thought they were talking about having sort of like I guess this is early Apple intelligence, but having a sort of model agnostic architecture.
You can right now, and I've actually got this enabled on my phone, you can enable ChatGPT. And if you make a request to Siri and you just simply say you want it to go to ChatGPT, it will. But there's too much friction around it. You have to tell it to go there. And second, it tells you it's going to go there, and there's a longer delay and all that sort of stuff. But I basically refuse to use Siri as is and go to ChatGPT every opportunity I can, even when I'm using the voice mode on the iPhone.
Okay, Apple, catch up.
Yeah, you better catch up. All right, Zizi, what do you have for our last topic?
So another model release from Google I/O is the video generation model called View 3. And I was able to play with it, and I had fun generating fake podcast videos, like two persons talking.
I saw some of those in Slack.
Those 8-second clips. So what's the most stunning is that, not only the visual quality, but also the audio and the lip syncing quality. Yeah. And sometimes, if you wanted to generate a short clip of a baseball game, it will generate, the video with the background noise, like the crowd cheering.
Yeah, I think the one you posted, it was like, the video was beautiful, but like the sound of the ball being hit by the bat happened like
when it hit the net.
Right. It was completely out of sync.
Right. So I think it is, much better than the previous generation of models. However, the physics is still oftentimes broken. So, for example, the podcast video clips, while it looks pretty natural if you look at one speaker, but the other speaker is also moving the lips. So it's it's still not quite there, but I'm pretty excited about the progress. If you
if you
think about how short the timeline
how
is,
fast these cycles are, and the quality of the video. I saw a bunch on X, Twitter, and they were all labeled like 100% AI generated, and had that label not been there, I would have had no idea.
Crazy.
Yeah, it really, really is. All right, guys. Well, this was, another month in AI. My God, it's moving fast. I really, really appreciate you guys being here today. This was a fun one.
Thank you so much. Glad to be here.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.